Hi, here we are discussing about a project accumulator-based 16-bit processor for wireless sensor network. So this project is discussed about a accumulator. It's a critical register within a CPU used to store intermediate result during arithmetic and logical operations. So enabling efficient data processing by holding this results temporarily, the accumulator reduces the need for repeated memory access, thereby speeding up the executions of instructions. It plays a central role in most arithmetic and logical unique operations, making it essential for efficient and streamlined processor performance. For this proposed approach, this project is developed with a dual accumulator, and this paper presents optimized with a reduce instruction set computer architectures that leverage a dual accumulator design to enhance the computational efficiency and performance. So this architectures is scheduled to support advanced memory management and peripheral operations, and addressing the growing need for high-speed data processing in embedded systems. The dual accumulator approach allows for parallel executions of the arithmetic operations, reducing the number of instruction cycles and improving overall throughput. This architecture is designed with a focus of optimizing area, delay and power consumptions, making it suitable for resource constrained environment. The proposed designs is implemented using Verilog HDL and synthesized on Xilinx Vivado platform, targeting the Zynq FPGA. The architectures performed is verified through extensive simulations in Modelsim, and the comparative analysis is conducted to evaluate the importance in the key parameters such as area utilizations, processing delay and power efficiency. The result demonstrates that the optimized dual accumulator based RISC architecture significantly outperforms traditional single accumulators design, so making it an ideal solution for modern embedded applications that require both high performance and low power consumptions. Now we can verify the paper. So this paper is purely developed with a 16-bit processor. That processor architectures we have developed with a novelty based dual accumulator design. So here we have taken this paper as a reference. So the architecture given in figure 2. So this is a two-stage pipeline accumulator based processor. So additionally we have used this paper architecture. So this is a reversible processor of 16-bit architectures, and we have merged with this two concept, and also we have added two accumulators in this design. So additionally this concept added with the instruction memory bus and also for peripheral memory access. So here this work we have developed within Verilog HDL and synthesized Xilinx FPGA. So here why the dual accumulator? So this interactions of dual accumulators is a processor architecture significantly enhance its a computational capability of enabling parallelisms, which is critical for improving performance in modern embedded systems. So with the two accumulators, the processor can execute multiple arithmetic operations of logic operations simultaneously, so effectively doubling its throughput for certain tasks. The parallelisms is particularly benefit in applications that require intensive data processing such as digital signal processing, real-time analytics and cryptographic computations. Moreover, the use of the dual accumulators reduces the instruction cycle time by allowing the processor to handle the complex operations more efficiently, so distributing the workload across both accumulators rather than the processing operations sequentially. So this is not only speed up execution but also optimize the utilizations of the processor resource such as arithmetic logic unit, leading to better overall performance. Additionally, the dual accumulator provide the great flexibility in the design of instruction set and optimizing instructions pipelines, further contributing to the efficiency and the speed of the processor. So here for the instruction executions we have used this Excel sheet. So here we have updated around 40 instruction cycles. So the first instruction cycles come up with the accumulators 1 and 2, and the second set of instructions come up with the register D and register S, and third set come up with the memory access and peripheral access, and fourth set come up with the branch registers. So as per that we have developed it, and this is a totally 16-bit processor. So for that 16-bit processor we have used here register D and register S and immediate values. Okay, this is all the 16-bit, and the opcode we have used for 6-bit. Okay, so here this work will verified in the Verilog HDL. Okay, so here, so this is a test bench of the coding. Okay, so here we have used this instructions in the opcode. Okay, so here, okay, you can verify the case statement. Okay, the first instruction start with register D and register S, register D minus register S. Okay, register D plus immediate, register D minus immediate, and 0 minus register D XOR register S. Okay, register D XOR immediate, and register D multiplications register S, and divide register D. Okay, and this is a memory exchange. Okay, so and accumulators value moving the register S data to accumulator 1, and moving the register S data to accumulator 2, and register S plus accumulator 1, and the output given to the accumulator 1. Okay, so and this is one for accumulator 1 subtract to the register S and moving the value to the accumulator 1. Okay, so as per that we have handled then 40 instructions. Okay, so 40 instructions we have executed. Okay, so these instructions will be given one by one. Okay, and this is a top model of the architectures. Okay, so here you can analyze the dual accumulator processor design of 16-bit. Okay, so here input we have handled the clock, reset, instruction data memory bus, peripheral bus, instructions enable, instruction done as output, and instruction data output. Okay, data memory write enable, write address, and bus output, and peripheral bus output. Okay, so here it will be start with the number of model. Okay, instruction fetch, registers, control logic, accumulator 1, accumulator 2, multiplexers, and multiplexer 2, ALU, branch registers, and program counter, and some of the multiplexers also we have added. Okay, so as per this executions, here we have simulated the tool in Modelsim. Okay, so here you can analyze the op count and the parallel output. Okay, so here these are the instructions. Okay, so here register D plus register S. Okay, so that is the first instructions we have given in the test bench. Okay, so this one register D plus register S. So here register D and register S we are given 64 plus 45. Okay, so here it will be given. Okay, so this register D and register S, it will be moved to the ALU. Okay, through some multiplexers. Okay, after that it will be add the logic. Okay, so here you can analyze it, register D and register S. Okay, so it's come with the ALU. Okay, so then it will be added here. Okay, so then we are taken our final output O data D equal to 109. Okay, so here 64 plus 45 equal to 109. Okay, so this output it will be moved to the output data memory. Okay, so the multiplexers, then it will be moved to the invert logic. Okay, and finally it will become with the instruction output registers 109. Okay, so this is a overflow of the architecture. Okay, so here, so the ALU output goes to the multiplexers. Okay, and after it will be moved to the invert control logic. Okay, and then the final output given to the instruction fetch. Okay, so the instruction fetch will provide the final output. Okay, so here the instruction fetch, first of all it will receive the data and it will bypassing the value to register D and register S to this registers, and the control logic will operate all the functionalities of the instructions. Example, the ALU operations and branch operations. It will be decision making process. It will be happen in the control logic. This is a control logic code. Okay, and here here. So the ALU, it's doing a addition, subtraction, multiplication process, and branch registers also it will be doing the conditions parameters. Okay, so here the branch instructions means, so here it will be applicable. Okay, so register D we are checking. Okay, so it will be greater than 0 means we need to add the offset value plus the branch registers. Okay, and the final output given to the branch registers. Okay, so as per this reference, the similarity of this executions of arithmetic logic instructions and the branch registers execution branch instructions. Okay, so we'll develop this works. Okay, so here the next instructions means it will be come with 88 and 44. Register D is equal to 88 and register S equal to 44. Okay, so next instructions is subtractions. Okay, so register D minus subtractions. Okay, so here the output come with 44. Okay, so here the next instruction and next instructions we can check it. Okay, so here next instruction says 12, right? So register D is 12 and the immediate is 24. Okay, so we'll add the value register D plus immediate. Okay, so 12 plus 24 equal to 36. Okay, so here this is an inversion execution and this is a multiplication execution. So 46 into 2. Okay, so here 46 into 2, so it will be present, output will be present with the register S. Okay, so register D will be holding the MSB data and register S means it will be holding the LSB data of the multiplier. Okay, so why? Because here we are using 16 to 16 multiplier, it will be provide 32-bit output. Okay, so that's why we will be splitting the LSB and MSB concept here. Okay, and after that memory exchange and divide by 2 process. Okay, and so up to this red line, red cursors. Okay, so we'll be execute the first set of the executions of register S and register D functionality. After that we'll be started the accumulator process, accumulator 1 and accumulator 2. So here this is the accumulator 1 register and this is the accumulator 2 registers. Okay, so here we have used the accumulators code. So this is the accumulator 1 and accumulator 2 code. Okay, so this is the process of accumulators. Okay, for checking purpose we have used this accumulator registers in the top. Okay, so here the 67 will move to the accumulators. Okay, and 42 will move to the accumulator 2. Okay, so that is the instructions here we had used. Okay, so here register S move to the accumulator and register S move to the accumulator 2. Okay, and the accumulator 1 plus register and move to the accumulator 1. Okay, so in that case it will be added. Okay, so accumulator here. Okay, so here accumulator 1 plus register D and it will be moved to the accumulator 1 plus register S. Okay, so here this instructions. Okay, so this instruction means already the 67 it will be available. Okay, so 67 plus 4 it will become with 71. Okay, so that 71 value will be present in the accumulator 1 registers. Okay, the same way we have developed it, and this is all the memory and peripheral access. Okay, so for memory and peripheral access, we are using this bus output and peripheral input. Okay, and so here the memory access we are using for data memory, write enable, write address and bus output. Okay, so this is all the instructions. Okay, so here we are writing the data into the memory and here we are reading the data into the memory. Okay, so this is a reading process. Okay, and this is a reading process and this is a writing process. Okay, and this is a branch instructions executions. Okay, so here these are the branch instruction executions, so it will be affecting the branch registers. Okay, so this is a branch registers executions. Okay, and after that we will be started parallelly with the program counter. Okay, and this processor design we have synthesized using a Vivado. Okay, So this is a Vivado executions. Okay, so here the post synthesis and simulations with the table comparisons. Okay, so here LUT it will be occupied at 2726. Okay, and flip-flops it will be occupied with 499. Okay, and IOB it will be occupied with 173 and FFG, and these are the power. Okay, on-chip power consumptions. Okay, summary. Okay, total power occupied with 0.136. okay, the pulse with occupied with 4.5 nanoseconds. Okay, and RTL schematic you can verify it here. Okay, so this is the RTL schematic. Okay, so peripheral bus, data memory bus, instruction data, instruction enable. Okay, so this is a register, multiplexer, branch registers, program counter. Okay, accumulator. Okay, and ALU, multiplexers, memory exchange unit, and multiplexers, invert control logic, instruction fetch. Okay, control logic. Okay, and second accumulator, mux4 peripheral select and mux4 memory select. Okay, and finally we are taken as a output. Okay, so as per the instructions we can write any coding for this processor. Okay, so if you are added the logic or any some algorithms, we can write it easily with support of these two accumulators. Okay, and for this project we have developed a abstract document with a report. Okay, so here you can analyze it, the title, base paper abstract, improvement of the project, proposed abstract, existing system, disadvantages, proposed systems, key features, introductions. Okay, advantages with related notes. Okay, and finally come with literature survey. Okay, and references. Okay, thank you.